All right, so welcome back, everyone. And it's a pleasure to have Jan Biringer giving his fourth lecture. So, okay, all yours.
Thanks very much. Yeah, so we're going to talk about Benjamini-Schramm limits of finite volume manifolds today. And the guiding question is going to be, so what's written on the screen, how do like invariants of spaces, I mean, really the invariant we're going to talk about today is Betty numbers. So how do these behave with respect to Benjamini-Schramm convergence? And this paper, or the talk that I'm going to give is basically on this paper with Miklos Abert, Nicolas Bergeron, and Tzachik Gelander. I mean, I guess it came out in maybe the end of 2019, and yeah. So yeah, so as always, please interrupt me with any questions you have. Oh, and let me start up the chat again. Yes, and I will definitely share my notes at the end of today's talk if you'd like. So
that would be great. Thanks.
Mm-hmm. Yeah. So okay. So right. So this is the question for today, and I just wrote a little bit of the background out so that we don't have to write it in real time. So let's just. So I assume Miklos talked about Benjamini-Schramm convergence of graphs, at least. I'm not sure if he talked about simplicial complexes, but and I talked about it in the Riemannian setting. And so let's just recall, like, here's the setup for simplicial complexes. So as always, you take some space of pointed geometric objects. So in this case, simplicial complexes, and then any finite complex gives you a measure on this space of simplicial complexes. Just by pushing forward the counting measure on the vertices, and then we say that the sequence of finite complexes BS converges, Benjamini-Schramm converges to some measure mu on K if when we take these mu Ki's and rescale them to be probability measures, then they converge weakly to mu. And last time we defined BS convergence of finite volume Riemannian manifolds similarly. So it's just like everywhere above, you take your simplicial complexes and you replace them with Riemannian manifolds. And you replace the counting measure on the vertices of a complex with the natural Riemannian measure on the manifold. Okay. So that's the little recap. So the starting point of today's talk is going to be this theorem of Elec. And I think this was from 2008. And so what he proved is that, so let's suppose that Ki is a sequence of bounded degree complexes. So here, like, the degree of a complex is just the number of simplices containing, the degree of a vertex is the number of simplices containing that vertex. And bounded degree just means there's a uniform bound on that over all vertices and over all I. And let's assume that we have such a thing that BS converges. Okay, so here bounded degree was there exists a uniform upper bound for the number of simplices containing a vertex. So uniform over everything. Okay, and then the conclusion is that so if you look at the kth Betty numbers of the Ki's, and then you divide out by the volumes of the KIs, then this converges for all K. Okay, where, you know, I'll remind you, as above, I think I set it up above here, but the volume is just the number of vertices. Okay, so here vol just equals number of vertices, and then bk is the dimension of the kth homology. And then we call these ratios bk over vol is, so this is the kth, like, normalized Betti number. Okay. So, right, so maybe some remarks about this. So what does this mean? Sorry. So this theorem says, in some sense, that that you can guess like the normalized Betti number of a space of a complex if you sort of sample the, like, geometry of K in large balls around sort of randomly chosen base points. Okay, and so, like, the title of Gabor's paper is Betti numbers are testable. So and you can think about this as saying that this ratio here, these normalized Betti numbers, are testable. Okay, and so, you know, sort of the intuition here is just that you know, sampling, you know, when you're sampling the geometry of K in large balls around random vertices, what you're really doing is you're sort of pinning down the measure mu K up to, you know, up to small error. And this theorem here is saying that you know, if you have a Bias convergent sequence, then the sequence of volume normalized Betti numbers converges. And so what that sort of means is that if these measures mu Ki over vol Ki are close to, like, this limit measure here, then these normalized Betti numbers should be similar. Okay. Yeah. So, right. So, any questions about that? So this is saying that the ratio then is testable. Let me leave you with that for once. I'll be back in 1 second. Okay. Okay, my apologies. So, right, so that's the first remark. Any questions on that? right, so maybe for a second remark, so if Ki here goes to mu, then you can view this theorem as a sort of giving a definition of the normalized Betty numbers of mu. Okay, so namely, the theorem is saying that that whenever you have a sequence, the normalized Betty numbers converge, and so you can sort of regard the limit as sort of a definition of the normalized Betty numbers of this limit measure. And I should mention that so Schrödel in 2018 also shows how to define such an invariant, for an arbitrary unimodular random complex. In a way that's sort of that's continuous under weak limits. At least for Sophic random complexes. So here, Sophic exactly just means like it's the Benjamini-Schramm limit of finite complexes. So, so in particular, that applies like anywhere that you'd want to be using Ellic's theorem. Okay, so he's able to give some sort of intrinsic definition of like a normalized Betty number for a unimodular random complex. So that those are, in particular, any complex that arises as the BS limit of a sequence of finite complexes. Okay. And then maybe the last thing that I want to say about Ellic's theorem is that it's really not true without the degree bound. And I don't know. I mean, there are lots of examples that you can make. Here's one. So I could just take I could make a finite complex. I mean, really just a finite graph, say that's of the form. So maybe I just connect like I vertices in a line. So this is like I vertices, and then I'm drawing you the graph Ki. And then at the end of this segment, I draw maybe a complete graph. So this is, let's say that this is like a complete graph on like Ni, which I'm taking to be much less than I vertices. Okay, and then if you take this to be your Ki's, these to be your Ki's, then because the number of vertices that are happening in the complete graph here, or really anywhere near the complete graph, is much less than I, then this BS converges to just the atomic measure on the graph. That's just a copy of R. So I mean, it's an infinite line. So all right, so that converges, that BS converges, but then you can go and calculate the Betty numbers of this, and like the first Betty number of Ki over the volume of Ki is like okay. I mean, I think you can just calculate this thing. And well, maybe I'll just say, right. So what is it? It's, I guess on the top, if you do the calculation, it's essentially like the number of edges the Benny number is for a graph. And I think it's like ni choose 2 minus ni. Like the edges that are coming from the line segment don't contribute to the first Benny number. And then you just like you collapse a maximal tree in the complete graph that sort of kills ni edges, and then you're left with this number. So that's the first Benny number, and then the volume here is what, like I plus ni, or maybe -1 if you're yeah, if the I counts the last vertex. Okay, but then the point is that what is this thing up here? So the only constraint on this really is that so this just has to be you know, like a lot less than I squared, okay? And this is like around I. So, you know, by varying ni, then I can get the top to be anything that's much less than I squared, and the bottom is going to be something around I. And so, you know, if I vary the ni, then these ratios can accumulate onto just all of R. Right. And so maybe let me just highlight, like, what's the feature here that's making this possible? Well, the issue is that the Betty numbers of you know, a complete graph aren't linearly bounded by volume. Okay, so what's happening here is that, like, you know, if I look at first Betty number, then the first Betty number of a complete graph on you know, I vertices is like I squared. Okay, and then, you know, you get even worse bounds if you look at higher, well, well, okay, so it's I squared here. And so what that allows you to do is it allows you to sort of just, you know, if you take your favorite BS convergent sequence, then you can sort of stick one of these complete graphs in it somewhere and just and alter it, and in such a way that it alters the normalized Betty numbers to be sort of whatever you want. Okay. Any questions? Okay. All right, well then, you know, the question today is, you know, is there a similar theorem for Riemannian manifolds? Like something similar to Ellic's theorem? Well, so the first observation is that, you know, you need something like a degree bound even in the Riemannian setting. And the reason is that, you know, again, you can construct Riemannian manifolds that have really small volume and like Betty numbers as big as you want. So, you know, since there exist Riemannian manifolds with small volume and huge Bettys, right? I mean, you know, this is sort of even more trivial in the Riemannian setting than in the graph setting, because, you know, because if I have any Riemannian manifold, then I can just scale the metric down so that the volume becomes infinitesimal, and that doesn't alter the Betti numbers. So really, I can have simultaneously whatever Betti number I want for a manifold, and whatever volume that I want for a manifold. Okay, so then you can find small volume manifolds with whatever Betti numbers you want, and then you can ruin a sort of Ellic's theorem by just sticking those into sort of pasting those onto whatever sequence of finite volume manifolds you want. Okay. So yeah, but so what is a similar theorem in the Riemannian setting? So this is a theorem we'll cite Ellic, Bowen, plus some help from our paper. And the theorem is if Mi is a BS convergent sequence of, say, closed Riemannian D-manifolds with sectional curvatures in like some interval, some compact interval. And also injectivity radius at least some epsilon, some fixed epsilon greater than 0, then these ratios bk of mi over vol mi converge for all k. Right, and so we talked about injectivity radius maybe 2 times ago, but when I say injectivity radius of a manifold, this is like the inf over all x in the manifold of the injectivity radius of m at x. Right, which is the, okay, I mean, I guess in this generality, I have to say it's the largest radius on which the Riemannian exponential map is injective. But just think, basically, it means that, for instance, that the, so the assumption above means or implies that each epsilon ball in like each mi is a topological ball. Okay. So each like metric epsilon ball is a topological ball. And the combination of that together with this sectional curvature bound, that's the sort of replacement for the degree bound in the complex setting.
I have a question about the sectional curvature getting bounded in an interval. So is that supposed to be negative numbers only, or can be anything?
It doesn't matter, actually. I think, just they have to be bounded.
Okay, thank you.
Mm-hmm. So, right. So let's talk briefly about a proof of this theorem. Not because this theorem is really the target of the talk, but because the proof ideas will be used later. So, right. So if I have a manifold, then an epsilon net in some manifold M is, so it's a maximal subset like S in M with the distance between X and Y at least epsilon for all X, Y, and S. Okay, so just a maximal set of points that are spaced out at least epsilon from each other. So whenever I have an epsilon net, then the epsilon balls like B, X, epsilon, X, and S, so they cover M. Okay, they cover M because it's essentially coming from maximality. If they didn't cover M, then you can find another point to extend S. And then you can define a complex called the nerve complex. So the nerve complex S, like N of S. I mean, in some sense, this should really be N of S comma epsilon, but I'm just going to write N of S. So this is the complex with vertex set S. And a K-simplex for every K-fold intersection of the balls B, X, epsilon. Okay, and so just the picture to have in mind here. Oh, somebody asks, why isn't this positive lower bound on injectivity radius enough? Yeah, it's not enough because you can still sort of right, you know, even if I have like injectivity radius at least 1 everywhere or something, if the curvature is really awful, like if the curvature is like close to negative infinity or something, then I can still pack like a huge number of like 1 balls around the boundary of this of a given 1 ball to sort of create something that looks like it has high degree. So, I mean, injectivity radius is not enough to like injectivity radius is not the exact analog in the Riemannian setting of a degree bound. It's in injectivity radius like with a sectional curvature, with bounded sectional curvature, that's sort of a degree bound. So, right, and so the picture of the nerve complex is just the following. So let's say that I have like these 4 points or something, and then maybe the epsilon balls around them look like this. Okay, so then the nerve is going to look like, I mean, let's say that there is sort of barely drew triple intersection there, but let's say that there is triple intersection. Maybe I can make it a little bit better. So there we go. So, right, so then there's an edge connecting those 2 vertices because their balls intersect. There's an edge connecting those 2 because their balls intersect, and 1 there, and also 1 here. But then there's also like this filled in 2 simplex here because all 3 of those vertices intersect. Okay, so this is and then this is the nerve. All right, and then the point here is that so the nerve lemma says that if the injectivity radius of M is at least, I think I actually need 2 epsilon here, then the nerve complex is homotopy equivalent to M. Okay. And so so in particular, the Betty numbers are the same. Right, and so this is a way to sort of discretize a manifold. Like you pick an epsilon net and then you sort of convert it into this nerve complex, which has the same Betty numbers. So, right. Yeah, so maybe right. So let's now prove or sort of sketch a proof of the theorem. Maybe just to make my notation simpler, so I don't have to write epsilon primes or something. Let me change the epsilon in the statement of the theorem to 2 epsilon, which of course doesn't make any difference, but allows me to say epsilon net below instead of epsilon over 2 net. All right, so here's the proof of the theorem. So what you do is so the idea is to randomly choose. So remember we're, right, so we have these MIs that BS converge to something. And then we want to show that the BKs over the volumes converge. And so the idea will be to just discretize the situation and use Ellic's theorem. So what we do is we randomly choose an epsilon net SI in MI and construct, right. So there's a question, how do you randomly choose an epsilon net? And the general strategy is you sort of superimpose a bunch of Poisson processes. So Poisson process is a way to randomly choose a sort of locally finite subset of a manifold, and sort of if you sort of choose a locally finite subset and then sort of put another one on top of that and another one on top of that, and then throw out any points that are too close to each other, then you can construct an epsilon net, sort of in the end. Although you might have to superimpose sort of infinitely many of these Poisson processes. Okay, and then you construct the nerve, like n of SI, of the corresponding cover by epsilon balls. Okay, and then the nerve lemma implies that this is homotopy equivalent to MI. So it has the same Betty numbers. And the assumptions on well, it's like the injectivity radius assumption, which we sort of need to make any of this work, and also the sectional curvature assumption imply that n of SI has bounded degree. Okay, so yeah, you really need the sectional curvature assumption in order to conclude this nerve complex has bounded degree, like independent of I. Okay, so then what you do is you show these random complexes converge. BS converge, and use Ellic's theorem. Okay, and that's how you would like to get a handle of the normalized Betty numbers of the M's. So you just like discretize them, and then you apply Ellic's theorem to the sequence of nerve complexes. All right. So that's sort of this is like the Ellic and Bowen argument. So I guess the history of this is that Ellic essentially sketched this argument, didn't write it up, and then Bowen needed it for something, and so Bowen ended up writing it up in one of his papers. So yeah, but then the issue is that there's a like a gap in this proof. So there's a gap above, since it's actually quite subtle. To show that that the like epsilon nets produced here sort of vary continuously in some sense if you vary the manifold. Okay, so I mean this is like sort of not obvious at all. And so the little help from our paper that I mentioned is that as we sort of circumvent this problem by like not bothering to create full epsilon nets. So we construct sort of random like almost nets. And show they're good enough. So, okay, I'm not going to write anything more about that, but like the point is that, you know, the construction, the Ellic-Bowen construction is kind of delicate because you end up, in order to get an actual net, you have to sort of superimpose infinitely many Poisson processes to make sure that you sort of get near every point in the manifold. But what we do is we stop at a finite stage. So we sort of superimpose only finitely many Poisson processes, and we get something that's not a net, like it doesn't get within epsilon of everything in the manifold, but it hits enough of the manifold that its Betti numbers approximate those of MI. And that's sort of good enough to make this kind of argument work. And then this continuity issue that's there when you try to construct random epsilon nets is much easier to get to solve. All right, and you know, I guess maybe I should just mention that you probably could also prove this particular theorem like maybe more efficiently analytically without discretizing, but this particular method that I'm sketching here is important for the later stuff that I'm going to talk about. Any questions about this this theorem?
Yeah, yeah. Is there a problem with the volume?
Is there a problem with the volume? No, I mean, yeah, I mean, it's right. It's true that you have to relate the volumes of the manifolds to the volumes of the complexes that you're constructing. But yeah, you can do that, and it's not difficult.
But they are almost very constant. Or...
well, I mean, you can get that that the ratio between them converges, which is all you need here.
Okay, thank you.
Yeah.
I have a question.
Mm-hmm.
So when you're choosing the Poisson processes, I mean, the intensity parameter should depend on the volume, right?
Mm-hmm. Yeah.
Okay, you're varying that with the volume.
Yeah. Well, I mean, in some sense, the intensity. I mean, you're always choosing like intensity 1 Poisson processes. I mean, you're choosing them on spaces that have bigger and bigger volume.
Okay.
Yeah.
All right.
Cool. All right. So that's I guess that's all about this discretization process. So maybe what I'd like to do now is say, well, okay, so we have this theorem here. So this is saying that, right, this is giving you a condition for when you have like an Ellic type theorem. So namely sectional curvatures and injectivity radius bounded. But a lot of the spaces that we care about, if you're studying locally symmetric spaces, in particular, then a lot of the spaces that you care about don't have an injectivity radius lower bound. And so it'd be great if we could sort of find a way to weaken that, to remove like the injectivity radius lower bound. And that's what I'm going to talk about now. So we'll now restrict to locally symmetric spaces. So let's suppose that G is a non-compact simple Lie group, sort of the same setting as all the rest of my talks. And X equals G mod K is the symmetric space. Okay, and as always, like you can basically always just imagine that X is either hyperbolic space or SLNR mod SON. Okay, and then as always, we say that an X manifold is just a quotient. M equals X mod gamma. By some gamma acting properly discontinuously and freely by isometries. So, okay, so the question then is, well, do you have an Ellic theorem just in the context of X manifolds? And if you remember, like we saw that that if you just look at random arbitrary complexes or arbitrary Riemannian manifolds, there wasn't an Ellic theorem, and the problem was that that you could have like small volume complexes or manifolds that have huge Betty numbers, and then you can sort of patch them in to BS convergent sequences and get all sorts of weird stuff. And so the first indication that maybe in the X manifold setting you could have some sort of Ellic theorem is this theorem of Gromov. So Gromov proved that there exists some universal C, which is like depending on X, such that if M is a finite volume X manifold, so we have that the Betty numbers, the BK of M, they're all at most C times the volume of M for all K. Okay, so Betty numbers in the context of quotients of a fixed symmetric space, then Betty numbers are indeed linearly bounded by volume. So there's some hope that you could have like an Ellic theorem in this setting. All right, and indeed, our main theorem is the following. So this says, maybe I'll call this the Abbg theorem below. So it says, let's suppose that X is not equal to H3, and Mi is a BS convergent sequence of finite volume X manifolds, then indeed the normalized Betty numbers BK of Mi over vol of Mi, they converge for all K. Okay, so it's exactly an Ellic theorem for these X manifolds for these fixed X's, as long as X is not H2. Okay. So, yeah, so maybe just as a sort of toy case of this, let me remark that when X is H2, this is kind of trivial. It follows from Gauss-Bonnet. since if you have any hyperbolic surface S, then it satisfies. So if I look at the normalized first Betti number, the first Betti number is the only one here that there's any question of controlling, right? Because the only other relevant Betti numbers are B0 and B2, and they're both just equal to 1 for for orientable surfaces. So if I look at the first Betti number over the volume of S, then okay, so the top is just 2 minus the Euler characteristic of S. Either using classification or noting that the alternating sum of the Betti numbers is the Euler characteristic. And so Gauss-Bonnet implies that the bottom is 2 pi times the Euler characteristic. And so, if I simplify this out, then I get what? Then I get 1 over pi times Euler characteristic of S, I guess, minus 1 over 2 pi. Okay. And then the point is just that if you have some Benjamini-Schramm convergent sequence, then, I mean, the only thing, so either, so what are the options here? Then either the Euler characteristics go to infinity, or they are eventually constant. So, in either case, this thing up there converges. Okay, so this is just a consequence of Gauss-Bonnet. All right, so maybe so H2, the case of H2 is trivial, so maybe we should say a couple words about the case of H3. So why does this not work for hyperbolic 3 manifolds? Right. Yeah, I should say, I found this theorem kind of satisfying because, for the early part of my career, I was mainly only working in hyperbolic 3 manifolds, and this is a theorem that's about everything except hyperbolic 3 manifolds. So, yeah. So what's an example with x equals H3? Well, let's suppose that K is the figure 8 knot complement. Say. All right, how about just K equals the figure 8 knot? And then M is the complement. Okay, so figure 8 knot looks like this, and then you make the crossings alternate. I'm not skilled enough to draw it without erasing. So then it's well known that M admits a complete hyperbolic metric of finite volume. As do also the Dane fillings MI, which I'm going to set to be it's the Dane filling M1I for large I. Okay, so what are these things? So the point is that, here we create MI by attaching a solid torus to S3 minus like a neighborhood of K, an open neighborhood of K, along the boundary of this neighborhood, which is then a copy of it's a 2 torus. And you do the attaching so that the meridian of the solid torus is glued to a curve in the homology class of M plus IL in H1 of the boundary. So, right, so the picture, kind of explain what that means. So the picture is, here's your solid torus. So imagine the interior is filled with your favorite flavorful cream. And then here's the meridian is this curve here that bounds a disk. Which is 0 in H1 of the solid torus. And then, if you think about a little neighborhood of the knot, so that's looking like something like this, and then this sort of winds around K. And then, so these coordinates M plus IL, or M and L for H1, M is like the meridian of this torus, so it's this is M. It sort of just loops around the if the knot is going like this way, then the meridian sort of loops around this way. And then the longitude is some transverse curve that sort of follows the knot. And namely, the L is determined by, this is going to be 0 in H1 of S3 minus the neighborhood, which is isomorphic to Z times M. So M generates the first homology of this complement, and L is 0 in the first homology of the complement. And then I'm gluing this solid torus onto there so that the meridian gets glued to M plus IL. And so that it turns out that there's work of Thurston that implies that if you take the measures, work of Thurston implies that the manifolds MI, they Benjamini-Schramm converge to like the manifold M. So in other words, they converge to like mu M over vol M, where M is the figure 8 knot complement. Okay, I mean, Thurston didn't care about Benjamini-Schramm convergence, but the point is that the MIs that you're constructing here sort of, they converge geometrically to this to the figure 8 knot complement, and as a consequence of that, you get Benjamini-Schramm convergence. But then the point is that the way you've rigged it up here, the first Betti number of M is 1, because M is a knot complement. First Betti number of a knot complement is always 1. And the first Betti number of MI is always 0, since we're gluing 0 in H1 of the solid torus, so that's this meridian, to a generator M plus IL. for H1 of S3 minus the knot neighborhood. Okay, so somehow gluing on the solid torus kills all the homology that you see in the knot complement. And so you get B1 equals 0. And then you can violate the theorem by saying you construct this following sequence. So I'm going to draw you a little table. X manifold and then B1 over volume. So the first X manifold is like M1, next one's M, next one's M2, next one's M, next one's M3, next one's M, da da da. And then the normalized Betty numbers are, well, 0, and then 1 over volume of M, 0, 1 over vol M, et cetera, et cetera. Okay, and so the top ones, these BS converge because the MI's BS converge to M, and so you're just like interleaving this convergent sequence with the limit. And these don't converge. Any questions on that?
Yeah, I have a question. So I understand your example, but why is being constant negative curvature really the problem here? Can you explain? I mean, where exactly is the geometry going here? I mean, so you said that the problem. So I mean, your theorem works if X is not equal to H3. So but why is hyperbolic manifold the problem here? Because I don't see. I mean, I don't know hyperbolic geometry, so I don't see what exactly is happening here. I understand the example though.
Well, I mean, it's not even that hyperbolic geometry is the problem, right? It's that hyperbolic 3 manifolds are the problem. Yeah, I mean, I mean, in some sense, like the problem is this Dane filling construction. Like, I think there's a sense in which you could make precise that this is the only thing that can go wrong. So. Yeah, and I don't know, it's possible we could talk a little bit later, like when we're doing the proof, about sort of why. I mean, really, the question is, why does it work when you're not H3?
Okay.
And maybe that'll be a little bit more clear when we talk.
All right, thank you.
Yeah. All right. So first, before talking about the proof, let's just do a quick application. So let's suppose that X now has rank at least 2. Okay, so e.g. now X is like SLNR mod SON, where N is at least 3. So there was this theorem that we talked about 2 times ago, which I'll rephrase in the geometrically. So this says if MI is any sequence of finite volume X manifolds, right, so here I'm taking them to be pairwise non-isometric. Then MI BS converges to the atomic measure on just the symmetric space X. Okay, so this is the geometric formulation of saying that like mu gamma I goes to the atomic measure on the identity. So this is the theorem that we stated 2 times ago. And so as a corollary of that, you get the following, which is so if MI is as above, so any sequence of of distinct finite volume X manifolds, then the Betty numbers, these normalized Betty numbers, so this converges to the so-called kth L2 Betty number of this metric space. Okay, and so what we're saying here is that, yeah, you sort of, you know that, like, you know from our theorem that, you know, since MI is a BS convergent sequence, the normalized Betty numbers converge, but actually they converge to this this invariant that we understand. And I should say that you know, this star here follows for cofinal covering towers. So a covering tower is like M1, which is covered by M2, which is covered by M3, and cofinal means that the associated sequence of subgroups trivially intersects. And so if you have a covering tower of compact X manifolds, then this follows by, this is like a theorem of George and Wallach from 78, I believe. Or, you know, or sort of after the fact, this also follows from Luke approximation, which I think Miklos talked about. And you know, and such towers sort of exist for, well, such towers exist for all X, sort of by work of Borel and Malchev. And so then what's the proof of the corollary? Well, the proof of the corollary is that if I have any sequence of MIs, then we know by the theorem above that that any such MI BS converges to this atomic measure on X. And then what I can do is I can just interleave the sequence MI with a cofinal covering tower. And, you know, apply our main theorem of the talk. Okay, so the point here is that we know that whenever you have a BS convergent sequence, the normalized Betty numbers converge. We know that for certain sequences, they converge to the L2 Betty number. And therefore, if you have an arbitrary sequence, you interleave that with the sequence that you know about, and you get that you still converge to this L2 Betty number. Okay. All right.
So I guess, quick question. Yeah. For this particular statement, so long as, say, something like the conclusions of Stuck-Zimmer holds, does it go through, or is there something else that you need? I mean, do you really need symmetric space for this? That's the point.
No, you don't. Yeah, I mean, really, the general version of the theorem that we prove here. So, I mean, we prove something for. There's like two parts for it. I mean, one applies like just generally in pinch negative curvature, except in 3 dimensions. And then there's another part of it that applies for like non-positive curvature under certain assumptions that include something about the limit measure.
Okay.
Yeah. So I mean, right. Local symmetry is not really essential anywhere here. This is all just sort of Riemannian geometry. All right, so I guess in the last 10 minutes, let me just give you like a sketch of the proof. of like the main theorem. All right, so let's let Mi be a BS convergent sequence of X manifolds. And let me assume here that X is not H2 or H3. Okay, I mean, I need to assume that it's not H3 because the theorem doesn't work for H3, and we've already proved it for H2. So let me assume that it's not either of them. Right, and so then you want to show that that the normalized Betty numbers Bk of Mi over vol of Mi converge. All right, so the first thing we need to do is let's just define the thick-thin decomposition. So let's let epsilon be small, and let's set like Mi less than epsilon to be just the points X and M where the injectivity radius is small, so where the injectivity radius of X is less than epsilon. And then let's define the thick part to be the complement. Okay, so this is the thin part. This is the thick part. All right, so then there's sort of two steps here. So the first step is to sort of handle the normalized Betty numbers of the thick parts. So the first thing to say is that you can show that that if I just look at the thick parts of these manifolds, then the sequence of thick parts BS converges. Okay, I mean it's basically just because they are geometrically defined subsets of M. They're sort of forced to converge then. And so then what you can do is you sort of mimic that argument that I told you earlier, where you construct random almost nets in the thick parts in these MIs. You know, take nerve complexes to then get a BS convergent sequence of complexes. Like Ki. And then, so you can use some work of Galander to show that each Ki is homotopy equivalent to Mi. Sorry, to the thick part. And I should mention, like, you might think, okay, well, doesn't this just follow from the nerve lemma like we did earlier? And you know, this is sort of more subtle than the nerve lemma. It's much more subtle than the nerve lemma. Since this thick part here has boundary. That's sort of the problem here, is that the shape of the boundary is a little difficult to control, and that screws with applying the nerve lemma. And so there's a whole story, like you know, Sachik's early career was sort of all about proving this kind of result. All right, and so then you apply Ellic, and Ellic implies that the normalized Betty numbers of the MI, the thick parts converge. And from there, it's not hard to see that that in fact, instead of looking at the normalized Betty numbers of the thick part, you can look at the Betti numbers of the thick part, but then you can normalize by the volume of the whole manifold. Okay, so essentially you're trying here to say that the ratio of the volume of the thick part to the volume of the whole manifold converges. And so you can prove that, and then that translates the fact that the normalized Betti numbers of the thick parts converge into this statement of Betti number of the thick part normalized by volume of the whole manifold converges. Okay, so that's step one. Right, and then what's step two? Step two is you show that that adding back in the thin parts doesn't change the Betti numbers significantly. Okay, so the problem is that currently we know that the Betti numbers of the thick parts converge, but we want that the Betti numbers of the whole manifolds converge. And so we need to say that when you add back in the thin parts, then you don't screw up the numerator too much. Okay. All right, and so that you actually do in sort of two cases, depending on whether the rank's 1 or higher rank. So maybe I'll just say briefly. So if the rank of x is 1, like if you're in hyperbolic space, then so the Margulis lemma implies that each component of the thin part is either a d n-1 bundle over S1, where n is the dimension of x, or a product of its boundary times 0 infinity. And you can use that to say that when you add in a component of the thin part, then the Betti number is only changed by at most once, by at most 1. So gluing on such a component to the thick part changes. So this is just straight from Meyer-Vietoris. You can check that this means that it changes the Betti numbers by at most 1. And then the real point is that we can prove that in higher dimensions, so if the dimension is at least 4, the number of these components is like sublinear in volume, essentially. Okay, so you can't have too many components of the thin part, or you can't have a number of components of the thin part that's comparable to the volume if your dimension is at least 4. So that's sort of where we're using that it's not H3. Okay. So and sort of using this, then you can just say that if you look at the Betti numbers of like the MI, the thick parts over volume MI, and you look at the Betti numbers of the MI over volume of MI, these have to converge to the same value. Okay. So just to recap, the Margulis lemma is giving you that you know what each component of the thin part is. Sticking on such a component only changes the Betty numbers by 1 and the number of such components you can bound. Right. Yeah, so that's the rank 1 case. And then the brief explanation of how to do it in the higher rank case is as follows. Well, here, so in our locally symmetric space setting, then yeah, so here we know, like by Stuck-Zimmer, that the MI's BS converge to an atomic measure on X. And in particular, that implies that the volume of the thin part over the volume of M, of MI, is going to 0. So the point here is that, you know, actually the as we saw before, like the injectivity radius at most points of MI is going off to infinity. Like it's not small. And so in particular, you get that yeah, the set of points where the injectivity radius is like less than epsilon is going to 0. And then we can adapt arguments of Gromov that he used to prove that theorem that I mentioned earlier. To show that that if you look at the Betty numbers of the thin parts, and also, you know, I guess technically you also need to understand the Betty numbers of the boundaries of the thin parts for this to work. But those things are all bounded above by some constant depending on the volume of the thin part. Okay, so the Gromov argument said that the Betty numbers of M of like MI are bounded in terms of the volume of MI. We sort of translate that to a statement about thin parts. And then you just finish by saying, so, you know, gluing on MI, so gluing on the thin part onto the thick part, so yeah, so I mean the point is that because of this the fact that the ratio of the volume of the thin part to the volume of the whole manifold goes to 0, like this thing on the right of the inequality is like sublinear. Or I mean it's, you know, it's much less than vol of MI. So that means that gluing on the thin part onto the thick part sort of changes the Betty numbers by an amount that's much less than volume. And that's the end of the proof. Yeah. So I guess I'm done.
Okay, thank you, Jan, for the beautiful lecture. Are there questions for Jan?
Yeah, so there's one thing that I'm a little bothered about. I mean, so maybe this is, so say in dimension 4, and you have, say, something hyperbolic, and you try to do this sort of Gromov 2 pi filling, and you get something that's non-positively curved now. I mean, maybe you could construct a warped metric. So why is that not a potential counterexample? I mean, why isn't the so I mean the Thurston-Dane filling gives you this sequence which does not converge, but suppose you have a hyperbolic 4 manifold and you still try to do a Gromov-Thurston, say 2 pi filling on the cusp, and you're not going to get a solid torus, you're going to get a torus cross a disk torus of dimension 2 cross a disk. So you're going to get a non-positive curved manifold there. And then you continue doing this sequence of Dane fillings and you're going to converge to the cusp. I must be missing something here. So can you say something about that?
Okay, so I don't remember exactly how the it's been a while. So wait, how does okay, so you there's some way of filling in the cusp so that you get some non-positively curved manifold.
Yeah, it's something by Schroeder and somebody else from a while back. Maybe.
Yeah. Okay. Right. I mean, I guess our okay. And so then, all right, so then what are you saying? You're saying so presumably these things then converge geometrically to the
cusp manifold
thing.
Yeah.
Okay. Right. Yeah. Well. Right. I guess I'd have to see some. I haven't thought about that in particular, so I don't know. Right. I mean, you want to say that you can't do some sort of thing like with the figure 8 knot and actually make the Betty numbers drop or something.
Yeah. So maybe that's it's just sort of a sanity check that I wanted to run. So.
Yeah. No, I mean, I guess that's the point. I mean, I don't know off the top of my head why you can't drop Betty numbers in that situation. It's a good question. Well, I guess it's also worth saying that our theorem doesn't actually apply to that sequence. Okay. I don't think either, right?
Okay.
Because you're in non-positive curvature.
That's right. Okay. Yeah. So, all right. Okay. Very good. Okay. Fine. Fair enough.
Yeah. No problem. Yeah. Yeah, it would be interesting to sort of feel like understand what exactly is going on there, though.
Okay. Any further question for Yang?
Yeah. Can I want to ask a question about earlier parts. If somebody has a question about this, they can ask first. Yeah.
Yeah. Maybe you please go ahead.
Yeah. So, Ian, I just wanted to know. So you talked about invariant random subgroups where you took the G invariant measures, but one can take maybe some other group acting, some other automorphism group acting on the group G, and then you can talk about invariant measures on sub G under that action. Has anybody worked on this kind of thing? It would be somewhat different, right? So.
Yeah. I want to say yes. I don't. I never have, so I don't know in particular. Like, yeah, you might want to talk about like right. I mean, what would you be talking about? Like characteristic random subgroups or something? Like if you look at the automorphism.
No, not the whole automorphism group. Maybe some particular subgroups of automorphism group, like say even one automorphism and take invariance.
Yeah. I mean. Yeah. I mean, I guess I don't know of I don't know what theory really to point you to, but I'm sure that's totally a natural thing to do, and probably some people out there have been have studied it. Yeah, I don't know. I haven't tried generalizing in that direction, so
the characteristic subgroup will probably not give you too much more, right? Because it may be the same IRSs you would get, right? Because
yeah, well, I mean, you'd cut some out, I guess.
Okay.
Potentially.
Yeah, maybe some normal subgroups are not really correct, but
yeah, exactly.
But it would be subset of. Yeah.
That would give you a subset of IRSs, yeah. Yeah, right. That's a good idea for future research, or at least future Googling to see if people have already done it.
Future idea for Googling it. Okay.
Yeah.
Thanks.
Yeah, thank you.
Any other questions?
I had some earlier one question, but I don't remember. So maybe if I remember, I'll write to Ian and ask him later.
Yeah, great. Yeah, I mean, really, anybody feel free to email me whenever. So.
All right. So if there are no further questions, let's thank Ian for this wonderful set of lectures. And thank you, Ian.
Yeah, my pleasure. Thank you all.